Guys, today we're going to be going over mAs, which is in chapter 15 of our Physics Digital Age book. Oop, my stylus is messing up again. Okay. Now, mAs is made up of two factors. It is made up of mA, which is our milliamperage, and S, which is our time, which is going to be measured in seconds. And also remember that mA is quantity. It has nothing to do with the quality of our X-ray beam, meaning it has nothing to do with the energy or anything like that. Also, I want you to remember that mA is a technical factor. This is something we set at the control panel, and it's not a geometrical factor or anything like that, like what we have talked about in the other videos. Tube current is something you definitely need to be familiar with when talking about mA and mAs or anything like that. Tube current is going to be the flow of electrons in the tube. And the reason you're going to need to know about tube current is because tube current is measured by mA. Which is, don't forget, milliamperage. Now, we know that from other chapters and knowing the X-ray tube that the electrons are going to come from the selected filament wire, which we are going to select we want to select the small filament wire. The only time that I know of, there could be other times though, that we're going to select the large filament wire is whenever we're going to be doing chest or abdomen images. But as far as what we're doing right now, we're going to be having the small wire. Now, these electrons are going to be moving through this small filament wire at a high speed and causing friction and all that. And whenever they get in there, it's going to be causing thermionic emission. Now, thermionic emission is the boiling off of electrons. And we also know that once they boil off, they go into this space charge cloud. And they are held there due to oblique repulsion. And when KVP comes in and it gives these electrons that push they need to travel at a high speed to the anode to create our X-ray photons. Now, the reason I'm telling you that is because let's say this is our cathode, which we know is negative. And let's say over here is our anode, which we know is positive. Now, we know that the electrons are coming through here. Let's say they've already been boiled off due to thermionic emission. So we have this space charge cloud. And let me go ahead and put like a little thing right there, and that will be considered our oblique repulsion. Now, in the space charge cloud, there is going to be negative electrons all in there because they have been boiled off due to thermionic emission. And remember, you cannot have any more than the amount that you set at that control panel. If one comes in, then one will be going, if let's say one comes in, this one would be going back in. And remember that in the tube, it has 3 wires, one for the electrons to come out and one for the electrons to go back in the tube. But we have to keep an equilibrium. Now, the other wire, remember that I said there was 3 wires right here. That is for our KVP. Now, this KVP is going to give these electrons the push that they need to get over here to the anode. And we know that once they hit the anode, they're going to go through many different types of interactions to be able to create an X-ray for them to come down here. Now, this is why I'm showing you this tube current. these electrons traveling at a high speed, and remember that we know that it's only about an inch or inch and a half or somewhere around there between the cathode and anode. So they're traveling at a very, very high speed, and these like very high speed. And right here is where your tube current is going to be, because remember, your tube current is the flow of electrons in the tube. So while they're traveling across here at a high speed, that is what's going to be happening. And I want you to know, as we increase our try to undo that. As we increase our mA, that is going to increase our filament amperage, which increases thermionic emission, which is increasing the number of electrons created, which are available to flow across the X-ray tube and collide with the anode while creating X-rays. Now moving on. Alright, now going back down, talk some more about mass. I said earlier that mass is made up of two things, mA and S. We know that S is our time measured in seconds, and mA is our milliamperage. So to find our mass, because sometimes you're not going to be just given the mass, they might give you a problem where they only give you the mA and they only give you the seconds. All you're going to have to do to be able to find the mass is multiply these two, and then that will give you your mass. Now, let's say a problem only gave you your mass and your seconds. The way you'd be able to find this is by division, and then that would give you your mA. It's really not hard. It's very simple math, and you'll definitely get down to it. Now, one thing I wanted to explain to you is about mass is the relationship mass has between things. We remember that mass is quantity and it has nothing to do with the quality of our beam. So, if we increase our mA, which is our milliamperage, then that means we are going to be increasing our tube current. Now, if we increase our tube current, which we know is the flow of electrons in the tube, that means we are going to be increasing the electron flow, which of course means we are going to be then increasing the number of X-rays produced. So you could go ahead and say that if we are increasing mA, then that means we are increasing the number of X-rays produced. Now, if you double your mass, then of course, that means you're going to be directly doubling your intensity, which your intensity is the number of electrons going through per second. Mass also contributes directly to the exposure to the patient and IR, because remember, if we increase our mass, then that means we're increasing the number of electrons flowing, and which is automatically going to increase the number of X-rays produced. So of course that would mean that it's going to contribute directly to our exposure to the patient and IR. Now, one thing that can be confusing is mA and S, which is seconds, are inversely proportional. Sorry. Now, also, it's hard to kind of think about this, but you cannot think as mA and seconds are the same thing. Now, mA and seconds come together to make mass, but they are not the same thing at all. S is seconds, mA is milliamperage. But just know that they are inversely proportional. So which that means if I go up in my mA, then that means I'm going to be going down in my seconds. Now going back to the relationships again, I want you to remember that if you increase your mA, then that means you're going to be increasing the intensity Also, if we increase our mA, like we said earlier, that is going to increase your receptor exposure and your patient dose. Which that makes sense, like we talked about earlier. MA is the measurement of tube current, and we know that tube current is the flow of electrons in the tube. So if we increase our MA, then that means we are going to be increasing the amount of electrons, correct? Correct. Now the next thing I wanted to go to is whenever we select the filament, because remember that we are the ones that are going to select that filament. We want to pick that small, unless we are doing a chest or abdomen type of picture. Now, one thing I want you to remember is if we do not have enough electrons coming in, then that means it's going to have an underexposure in the image, and that's going to leave our image looking grainy and blotchy. And now grainy and blotchy, if our image comes out looking like that, then that means that you need to increase or it means you need to adjust your MA, not your KVP. You're needing to adjust your MA. And that has to go along with the quantum model. And I want you to know that a common cause of visible quantum model in radiographs is an insufficient mass setting. However, anything that results in an insufficient amount of exposure at the image receptor plate can lead to models, such as inadequate KVP to penetrate the part or rectifier failure in the X-ray machine. And that's just some little information. Now, what I wanted to talk to you about, and this is one of the last things, is whenever we are setting our time. Because remember, mass is made up of two things, MA and seconds, which is our time. Whenever we're setting our time, we want to remember that there is one thing that we cannot directly control within the X-ray room, and that is our patient. We can try as many things as we want to, but we cannot control our patient. Our patient also can cause blur. Due to what? Due to motion. Now, if our patient has an uncontrollable type of disease, like let's say they have Parkinson's. Like if they have Parkinson's, then that means they are automatically going to be shaky. Now, what we would want to do for that type of case is we would want to decrease our time. Because if we decrease our time, then that means when we'd be minimizing our exposure. If we're minimizing our exposure time, that will help reduce the blur in the image. And now if we're reducing the blur in the image, then that means our image might come out with better detail. Now, that is not a directly proven statement, but it helps. It helps. Like, so if we have a patient, let's say patient comes in and has Parkinson's, and that is a shake. We're just going to put shake. The higher our exposure time is the more we're allowing that patient to have that shake and allowing our patient to be able to cause blur in our image. And we do not want that. We want the least amount of blur. So for us to get the least amount of blur, what we are going to do is minimize our exposure time. So, what does that mean? Minimizing our time helps provide spatial resolution, which we know is image detail sharpness. Alright, and today that should be it. If you have any questions, please put them underneath in the comments. I hope that this helped a little bit. I know it was a little bit all over the place, but I hope that it helped.